Okay, thanks, Helmut. So this is a continuation of the talk I started yesterday. And we were talking about the Euler's equation on a fixed domain with sleep boundary condition, incompressible Euler equation with fixed domain on the with a sleep boundary condition. And so our goal at that time, yesterday, the primary goal was to demonstrate how to construct an unstable manifold, but that was really a reason to start all of this introduction of the Lagrangian formulation and so on, and see how this is going to help the analysis. That's amazing. How these structural observations can help us to do the analysis and overcome certain difficulties in the analysis. So we started to introduce Lagrangian coordinate, and the main thing is that the Lagrangian flow map lives on kind of like infinite dimensional Lie group of volume preserving maps on the physical domain. And this is, one can rigorously prove this is a smooth Lie group in the, as a submanifold in the function space of hk if k is bigger than half of the dimension plus 1. And the tangent space of this Lie group is the associated Lie algebra is exactly the space where the Euler equation is given in the Eulerian formulation. And then the advantage of doing this is that this transport term in the Euler equation disappears and then becomes a part of the second order derivative of the Lagrangian coordinate map. And so the Euler equation is written in the form that second order derivative of the Lagrangian coordinate map is equal to basically the gradient of the pressure composite with the inverse of the Lagrangian coordinate map. But so here, this configuration space is introduced as a smooth submanifold in the HK space. In other words, its differential structure is introduced by the HK space. Then we need a metric on that. And the metric, so when I write this down, this is imposed in the ambient space HK because UT is a tangent vector. U is on the configuration space. UT is a tangent vector, but the second order derivative is not tangent anymore. So we're going to have some metric structure to write this as equation on the manifold. So here the metric structure comes from the energy structure. So from the Euler equation, there is a conservation of energy. The conservation of energy is basically the kinetic energy that's half of the L2 norm square of the velocity. And but in the Lagrangian formulation, that's equivalent to the velocity of the Lagrangian map. So this is the conserved energy. So this tells us that probably it's more reasonable to choose the L2 norm as a metric. It's probably more reasonable to use the L2 metric on the tangent space of this configuration space. So then with the L2 metric, so here we see that the metric and the differential structure are based on different metrics. And this can potentially lead to some problem. So let's see. So right now, if we think about the L2 metric, then we think the tangent space of this Lie group as subspace in the L2 space instead of the HK space. And for example, at the identity, the tangent space of the Lie group, the configuration space is the phase space of the Euler equation in the Eulerian formulation. And this is the space of divergence-free vector field with non-sleep boundary condition. Okay, when we talk about the L2 vector field, so if we talk about L2 vector field and talk about its normal component, normally if we want to take trace, then the vector field should not be worse than H1 half, should be slightly better than H1 half. But however, if the vector field is divergence free, then it makes perfect sense to define its normal component as in H minus 1 half. So this is well-defined notion for divergence free vector field, even if W is only in L2. So it makes sense to talk about this tangent space in L2. And then when we think of this as equipped with the L2 metric, then we can think about its L2 orthogonal complement. The L2 orthogonal complement will appear later when we compute the Lagrangian multiplier. And the L2 orthogonal complement gives us the, if you just to do a simple computation, that's Hodge decomposition basically, it is given by the gradient of a function. So it's given by gradient vector field. And this is well known that the orthogonal complement of divergence-free vector field is just the gradient vector fields. But in the Lagrangian formulation, everything needed to be composite. You decompose the Lagrangian map. Okay, so we have this decomposition. But now, at this moment, we should keep in mind that is the configuration space is a smooth manifold as a submanifold in the HK space with induced differential structure coming from the HK, because we do need those things to define the volume preserving notion in a convenient way. But the metric, the Riemannian metric on the tangent space here is given by the L2 metric. So the Riemannian metric induces a much weaker topology than the topology induced by the differential structure. And then let's continue with this. Then from the conserved energy, there is a conservation of energy, which is basically the kinetic energy. And then one can perform a Lorentz transformation and come up with the Lagrangian. So the Lagrangian is functional defined on the tangent bundle of the configuration space. And this is exactly just the L2 norm of the tangent vector field of the Lagrangian, the configuration space. So from the Lagrangian, it looks exactly like the energy, but that is only because there is no potential energy in this case. And then we can define the action. So I'm right now following a standard recipe in the Lagrangian mechanics. Then from the Lagrangian, we can define the action for any path. Right now, we are just doing this, say formally. Think about a C1 path on the configuration space. And then you can compute the Lagrangian evaluated at U and the partial U, partial T, and integrate in T. So this is the action. And the minimum action principle says that one should consider the critical path. So the critical path, you do the variation over here. So that is basically the variation over here. That's UT squared. Then when you carry out the variation of this functional, the action, the integral of UT squared, then you do integration by parts in T once, and assume that when you do the variation, you don't change the boundary value, then you end up with this. So a critical path would say that U is a critical path if and only if this is equal to 0 for any variation of vector field U tilde. And this doesn't mean that UTT must be 0, because so right now U tilde, the variation of vector field, must be a tangent vector field. So here U tilde must be in the tangent space at the tangent space of the configuration space at the point U. So this is this variation of vector field is not arbitrary. When this is not arbitrary, then this is not necessarily 0, but this has to go through all the possible tangent vector field. So this must have tangent component 0. So that is here. This must have tangent component 0, so it has to be exactly in the orthogonal complement of the tangent space. So as we just wrote on the last page, the orthogonal complement, L2 orthogonal complement of the tangent space of the configuration space is given by the space of gradient vector field. So at this moment, we see that the critical path satisfies this equation, and that's exactly the Euler equation we saw on the previous page. Okay, so this is Euler equation, and here the critical path satisfies exactly the the critical path of this action satisfying exactly the Euler equation. So Euler equation is a critical path of this action on the configuration manifold of all the volume preserving maps on the fixed domain. When we take the Lagrangian exactly just the square of the norm of the variational vector field, then this is the critical path gives you the geodesics, because this also tells you that the second order derivative has only normal component. So if you can consider the covariant derivative, then it must be 0. So you get the geodesic equation. So that is the Euler equation in this setting is the solutions to the Euler equation in this setting in the Lagrangian formulation corresponds to exactly the geodesics on the configuration space. Okay, so this observation had been made a long time ago in the 60s by Arnaud, and actually even before that. But we are going to, we want to see how this is going to help the analysis. So the next thing is that here, the pressure in this Euler equation appears as a Lagrangian multiplier. So it appears, the gradient of the pressure appears as the normal component of the second order derivative of the Lagrangian map. So it's a Lagrangian multiplier, but it would help if we can compute it. So from the equation, from the Euler equation, if you take the divergence on both sides, that's the first thing you get. That is minus Laplacian of the pressure is equal to the product of the first order derivative of the velocity field. So from here, it hints that the pressure should have one more derivative than the velocity field. And if this is the case, then gradient of the pressure has the same regularity as the velocity field. And so the gradient of the pressure becomes a regular driving force. So it's a driving force in the Euler equation at with the same level of regularity as the velocity field. And that would be very easy to handle in the, say, well-posedness analysis or some other analysis. But this is not enough. The Poisson equation is not enough. We also need the boundary condition. So you take the Euler equation and restrict it to the boundary and take the dot product with the normal component. Okay, and using the non-slip boundary condition, we can derive, so from the Euler equation, Vt plus V dot grid V plus grid P is equal to 0. Then you take the dot product with the normal component on the boundary. And when you do that, the first term drops out. The first term drops out, and this term gives you the normal derivative of P, which you want as a boundary condition determining the pressure. And there's one more term. There's one more term that's V dot gradient V dot N. So this term looks like it depends on one derivative of V. If that is the case, that would be bad because this is one derivative of P, and if this is comparable to one derivative of V, then you would be in trouble. But remember, V is only tangential. So you're taking a derivative in the tangential direction only. So then this becomes from just like apply the product rule, you get this is equal to V dot grad and directional derivative of the normal component dot V. And so this part, if you take the directional derivative of N, the normal vector, in the direction of V, that's a second fundamental form acting on V. So you get this term, which depends on the second fundamental form of the boundary, the physical boundary of the domain. And assuming that the physical boundary is smooth, then here, if the regularity of the velocity field is good enough, then it tells you that the gradient of the pressure is indeed one order derivative better than the velocity field. So putting these things together, you see that the gradient of the pressure is indeed nice driving force at the same regularity level as the velocity field. So motivated by this calculation, we can define for any vector field W1 and W2, we define a bilinear transformation. So the bilinear transformation is completely motivated by the above. Okay, so take this combination of the product of the first order derivative of W, the vector field, and then solve the Poisson equation, and also take the tangential component on the boundary, apply the second fundamental form, and take this as the Neumann boundary condition of F. Then we define the bilinear transformation to be to have the value minus gradient F. So in this way, the pressure term in the Euler equation can be written simply as B acting on V and V. Okay, velocity field twice. And this is a bounded bilinear transform on the velocity field B. Okay, and then in fact, this is also the second fundamental form in the Lagrangian formulation, the second fundamental form of the configuration manifold at the identity element. Okay, this is the infinite dimensional manifold, and this infinite dimensional manifold, if you equip the R2 metric on the tangent space, and think this in some weird way as embedded in the R2 space. Okay, and then you can compute the second fundamental form of this manifold. And if you evaluate the second fundamental form in the infinite dimensional space at the identity element, then that's exactly this B. Okay, so this calculation involves the second fundamental form of the physical boundary, which is a finite dimensional quantity. And it induces this bilinear bounded transformation, which works as a second fundamental form of the infinite dimensional space, infinite dimensional manifold at the identity element. Okay, so now let's continue. Then go to the Lagrangian coordinates. Then the second order derivative of the Lagrangian flow map is equal to the gradient of the pressure composite with the Lagrangian map. So that is the gradient of the pressure composite with this is wrong. This shouldn't be here. This should be the gradient of the pressure composite with the Lagrangian map. Okay, so this is the form of the Euler equation, but then you replace the gradient P by the bilinear transformation depending on the velocity. The velocity can be written as ut composite with u inverse, and then finally composite with u. So this is a new bilinear transformation. We call that calgraphic B. And this calgraphic B is exactly the second fundamental form of the configuration manifold of the Euler equation in the R2 metric. Okay, so think this as a manifold embedded into the R2 space and equip its tangent space with the R2 metric. Then this bilinear transformation becomes the second fundamental form of this infinite dimensional manifold equipped with the R2 metric. And so this equation looks like the second order derivative of u is only given by this vertical component, normal component. It does not have tangential component. So it means that its covariant derivative is equal to 0. Second order covariant derivative is equal to 0. So here the covariant derivative on a Riemannian manifold is when the Riemannian manifold is embedded into a flat space, then this really just means that you take the usual derivative then project it to the tangent space, to the tangent direction. Then there is only a normal component here. So after you project it to the tangent component, you get the covariant derivative in t of ut is equal to 0. This tells you exactly you have a geodesic equation. So the Euler equation is exactly a geodesic equation. And if you write it extrinsically in the ambient space, then the right-hand side is exactly the second fundamental form. And concretely, it is given by gradient P composite with U. And on the previous page, we said that this B, this bilinear transformation is a bounded bilinear transformation on the HK space. But here, after the composition, all of this composition, it's not immediately clear how good this is because composition is always dangerous. Looks like, so for example, if you think about Poisson composite phi, and if you do the variation here, if you do the variation in psi is perfectly nice. It still maps the, if you carry out a variation in psi in the HK, and then the result is also in HK. But if you take a variation in phi, and then, so if you compute the variation of this in phi, then you would get d psi composite phi, then act on d psi. And here you lose one derivative. So the composition is not the best smooth operation you would like in the function space. Okay, and here we have compositions everywhere. And this is not immediately clear how smooth this B is, particularly with respect to U. With respect to the velocity, UT is fine. It's a bounded bilinear transformation, but with respect to U. So this is a key claim here. This second fundamental form, the characteristic B, is indeed smooth in U on the HK space. It really does not lose a derivative. So this issue, somehow it appears, but it appears several times in this calculation if you do the variation of V. So if you take the variation of this whole quantity with respect to U, then you would have bad term coming from here. You would have bad term coming from here, but all of them eventually are canceled. And eventually, this is a smooth bilinear transformation. Bilinear transformation smoothly depending on U. The actual proof of this claim is in the Eulerian code, is somewhat in the Eulerian coordinates by using a Debye-Curl type estimate instead of doing this directly from this form. So you take the curl of this vector field and take the divergence of this vector field and show the regularity of the curl and the divergence and their variation with respect to U. And then eventually you can come up with the smoothness of the second fundamental form here. So if when this is true, then you are looking at U in the HK space, and UTT is equal to a smooth vector field on the space HK. So it means that it's a HK vector field smoothly depending on its argument in the HK space. So it becomes a infinite dimensional ODE. This should be G. So this becomes an infinite dimensional ODE, means that the equation is associated to a vector field defined everywhere on the configuration space. And the vector field is smooth on the, actually the tangent bundle of the configuration space. So it's an infinite dimensional ODE. Unlike PDE, PDE should be understood as densely defined, reasonably nice densely defined vector field in the infinite dimensional function space. But here, it's really a second order ODE, which is everywhere defined and smoothly depending on the location the vector field in the HK is. So it means that now you can apply all the those arguments in the ODEs in a simple way to get things you like. For example, the Picard iteration should be good enough to get a solution. So this is not an obvious thing to see because the configuration manifold, the differential structure is from the HK metric. And the second fundamental form is from the R2 metric. These two metrics are different. And the R2 metric is weaker than the HK metric associated to the differential structure. So for us at this stage, it's a little bit like a coincidence. So here we have the smoothness of the second fundamental form. So now in this point of view, this is the Euler equation on the fixed domain with no-slip boundary condition in the Lagrangian formulation is the infinite dimensional ODE on the tangent bundle of the configuration manifold. But how come the Euler equation is appears as a PDE in the Eulerian formulation? So that is because here there is the infinite-dimensional symmetry group acting on the Euler equation. The infinite-dimensional symmetry group is exactly this group itself. And so if you apply the right translation to the Euler equation, so meaning that if you take any solution to the Euler equation and consider, so if U is a solution, then U composite with phi is also a solution. So if U is a solution, you compose for any fixed phi in the Lie group, then you still have a solution. So this is a huge group of symmetry. There is an infinite-dimensional family of symmetries. These are exactly the relabeling symmetry in the Lagrangian formulation. And using this relabeling symmetry, which is as big as the configuration space itself, then you can reduce the problem to the Lie algebra or the tangent space of this Lie group at the identity element. And that reduction gives you the Eulerian form of the Euler equation. But however, this reduction depends on this operation, this symmetry action. But this action is not so smooth as we outlined here. There is a problem with the regularity of this operation. So due to this loss of derivative, conceptually, the Euler equation after this symmetry reduction from a second order in time, ODE on the tangent bundle of the Lie group, when it's reduced by the symmetry action to the Lie algebra of the configuration space at the identity, then it becomes PDE in the Eulerian formulation. Okay, and then come back. But so this Lagrangian formulation right now works very well. So it reduces a lot of complication when with the smoothness of the second fundamental form. But there is a price to pay. So one thing is that the configuration space, the working space becomes a manifold, and you are working on the tangent bundle of a manifold. That's one thing. Another thing is, previously we had a steady solution, and right now it's not a steady solution anymore. So a steady solution in the Eulerian formulation was a vector field, a special vector field. And the special vector field in the Lagrangian formulation, it induced a non-trivial Lagrangian flow. So this non-trivial Lagrangian flow, of course, as a solution to the, I forgot to change this. So the Lagrangian path associated to the steady vector field becomes, of course, first a geodesics, as any solution of the Euler equation is associated to a geodesics. But it is also an integral orbit generated by this vector field and the group action. So this is a vector field in the Eulerian domain, and it corresponds to a vector in the infinite dimensional space. It corresponds to a vector in the infinite dimensional space at the identity. And by the right translation, this vector can be translated everywhere to be a tangent vector along the Lie group. And then, so you have a vector field starting from here, starting from this one. By the right translation, you get a vector field, an invariant vector field on the Lie group, and then you have integral curves. So at the same time, a steady state is both a geodesics and an integral curve of the invariant vector field generated by V star. Okay, so it's a special path. That's the characterization of any steady state of in the Eulerian formulation. So now let's look at some implications. With the Lagrangian structure, we can talk about many things. So one thing is the symmetry and the conserved quantity. I mentioned this already. So from the standard Lagrangian mechanics, then we know that whenever we have a continuous symmetry group acting on the system and leaves the action invariant, then there is a conserved quantity. Or conserved quantity, they are associated to symmetry transformations, which leave the solutions invariant, which leave the action invariant. So for example, we have the conservation of energy. Conservation of energy is associated to the translation invariance in T. So that is useful, but we are very aware of it. But then the other thing I mentioned is the relabeling symmetry. The relabeling symmetry says that if you take any solution of the Euler equation in the Lagrangian formulation and compensate it with this volume preserving transformation of the physical domain, then this is still a solution. So here we have infinite dimensional family of symmetry. Okay, that's a huge family. And what are the conserved quantities associated to this family of symmetry? That's the transport of the vorticity. But the vorticity is not transported as a scalar as always. Okay, in the 2D case, the vorticity is translated, it is transported as a scalar. This should be omega. Okay, in the 2D, the vorticity is transported as a scalar. But in the higher dimensions, it's transported as a two-form. So when you have the velocity, when you have the velocity, you can also get the momentum. Here, when the mass is assumed to be 1, the momentum is one form, and with the coordinate exactly given by the coordinate as in the velocity. But it's a one form conceptually, that's different. So that's the momentum. And then you take the exterior differentiation, exterior derivative of the momentum, you get a two form. That's the vorticity. And then the vorticity is transported as a two form. And in the two-dimensional case, two forms are equivalent to scalars. So the transport of the two form becomes transport of the scalar. But in the 3 dimensions, this is a two form in the 3-dimensional space, then the transport is more complicated and it has a stretching term, the vortex stretching term. Okay, the same thing can be written in the higher dimensions. So this is going to be actually useful later, even in the free boundary case. So then all of this would have implications on the analysis of the Euler equation. So first, we see that when we have the velocity field, which is divergence free and it satisfies the non-slip boundary condition, you apply the Hodge decomposition to the velocity field. You can see that the velocity field is largely determined by 2 things. One is the vorticity. And when the domain has multiple components, so if this is the domain, but it might have holes. Okay, then the vorticity does not immediately determine the velocity completely. The vorticity determines the velocity completely only when you have a simply connected domain. Well, you can add a constant vector to V, but with a slip boundary condition, that's enough. So when the domain is simply connected, the vorticity determines the velocity. But when there are holes, you don't have, the vorticity is not enough. So there is still a harmonic part. The harmonic part is related to the circulation. Okay, in this case, you can actually compute that there is a conservation of the circulation along each of these interior boundary curve. So the boundary has an exterior component and interior components. Like in the 2D, you can compute the circulation. And the conservation of the circulation of the velocity field along each of these interior boundary components, they are conserved. And then the harmonic part in the 2D, in this case, they are kind of like conserved. They don't really evolve in T too much when you have the conservation of the circulation, and the circulation determines the harmonic part. So to analyze the Euler equation in the Eulerian formulation, that's how conceptually one can reduce the problem a lot to the vorticity. But this is in the fixed boundary case. And later on, when we talk about the free boundary, and this becomes only a part of the problem and becomes an easier part of the problem. And the harmonic part becomes a huge issue over there. And now, when the Euler equation is written as an ODE in the infinite dimensional space, then it's easy to get the local well-posedness. You simply do the Picard iteration. And you have the HK regularity, the same regularity as the initial data, and the smooth dependence on the initial data in the Lagrangian formulation. That's very important. So we have the smooth dependence of the solution on the initial data in the Lagrangian formulation. Then if you go back to the Eulerian formulation, then the velocity field is equal to the Lagrangian velocity composite with inverse of the Lagrangian map. Okay, and this is the issue. So if you know that you have a family of solution which smoothly depends on initial value, whose initial value smoothly depends on a parameter. So think of as a family of solution with a parameter smoothly depending on the parameter. And so the solution is smooth in the parameter in the Lagrangian formulation. But then if you look at the Eulerian formulation and you take the derivative with respect to the parameter, when the derivative hits partial u, partial t, you are perfectly fine. But when the derivative hits the inverse of the Lagrangian map, you lose some regularity. Okay, so the same thing, the smooth dependence on the initial data, the same thing cannot be said in the Eulerian formulation. So this is well known that the Euler equation in the Eulerian formulation, when you look at the dependence on the initial data, in the metric HK, and when you change the initial data, the solution is continuous in the initial value in HK, but not uniformly continuous. That was proved some years ago by Himonas and Michalek. So conceptually, the transformation from the Lagrangian formulation to the Eulerian formulation immediately explains this non-uniform continuity on the initial data. And then another thing is that one can, by treating the Euler equation as an infinite dimensional ODE, but constrained to the manifold of volume preserving maps. Okay, then if one relax the volume preserving constraint, then you get in certain way, then you get a compressible Euler equation. That becomes a penalization problem. And when you send the penalization to infinity, it means that any deviation from the volume preserving configurations to a general configuration, to a general diffeomorphism, it would cause a lot of energy. And if that penalization is infinity, then you should be constrained to the volume preserving maps, to the manifold of volume preserving maps. So that is the compressible to incompressible limit as the sound speed goes to infinity. And that was the idea behind the proof of Eben in the 70s. Of course, this can be done without using this formulation, but this formulation gives a very nice analog of the compressible to incompressible problem. And then this problem can be viewed exactly as like the elastic pendulum converge to a rigid pendulum in the ODE. When you have an elastic pendulum with the elastic constant going to infinity, the pendulum should converge to a rigid pendulum. And that's exactly the same mechanism in this case. And finally, this formulation, when everything when the Euler equation is converted into the Eulerian, in the Lagrangian formulation as infinite dimensional ODE, then the regularity issue we had disappeared when we were trying to construct the unstable manifold. Then we could construct the unstable manifold of the unstable steady state with hyperbolic eigenvalues. And that was done in the Lagrangian formulation. And so a steady state, a steady vector field in the Eulerian formulation corresponds to a path in the Lagrangian formulation. And the exponential dichotomy is transformed into exponential dichotomy in the Lagrangian formulation assuming the Lyapunov exponent of the steady vector field is not too large. Okay, because the change from the Eulerian formulation to the Lagrangian formulation involves composition, and the Lyapunov exponent of the Lagrangian map could enter into the play. So after we have an orbit here with exponential dichotomy, then we can construct the stable unstable fibers. And these stable unstable fibers, when converted back into the Eulerian formulation, you get the unstable manifold and the stable manifold of the steady state in the Eulerian formulation. So that was, the construction was done by Lyapunov-Perron approach in the Lagrangian formulation. So having said all of this, we saw that the Lagrangian framework helped us to understand the Euler equation in several ways. It helped us to understand the symmetry and the transport of the vorticity, and also the analysis related to the smooth dependence and the non-uniform continuous dependence on the initial data, the construction of the unstable manifolds, and so on. So that's for the fixed boundary problem. So we're going to move to the free boundary problem and think of this problem in the Lagrangian formulation and see how that is going to help us. Okay. The free boundary problem can be solved in various ways, in various different ways. So here is just one point of view. So here we consider a droplet of incompressible fluid in vacuum for now. So here, this is the droplet in the vacuum. And the fluid occupies a domain, omega t at time t. And this domain moves. The domain moves according to the restriction of the velocity field along the boundary of the domain. So that's the kinematic boundary condition. So the velocity restricted to the boundary becomes the velocity of the moving domain. Okay, and inside the domain, the Euler equation is satisfied and it's incompressible. And then on the boundary, we might consider the surface tension or there is no surface tension. So when there is no surface tension, the pressure on the boundary should be 0. And when we consider the surface tension, the pressure on the boundary is proportional to the mean curvature of the boundary. So in the n-dimensional space, the boundary is an n-1 dimensional hypersurface, and the mean curvature is a vector. Okay, and we dot the mean curvature is a normal vector. And we take the dot product of the normal vector with the mean curvature vector, you get the scalar mean curvature. And the pressure is assumed to be proportional to the mean curvature on the boundary when we consider the surface tension. But this proportionality has to be positive. Otherwise, the problem is ill-posed. So this is the free boundary problem of one fluid. And a two-fluid problem, interface problem can be also considered, but I'm going to mainly focus on the one fluid problem. But everything I said for the one fluid problem can be parallelly generalized to the two fluid in the same Lagrangian formulation. So in the two fluid case, there is a fluid. So there is one kind of fluid inside in the inner domain on the one side of the interface, and the other fluid on the other side of the interface, and they share the boundary, which is the interface. And so the kinematic boundary condition is still satisfied. That is, the boundary moves, the interface moves according to the velocity field restricted to the boundary. But the problem is that the velocity field from the two sides, when restricted to the boundary, they may not be equal. But that's fine. The interface is, the motion of the interface is actually determined by the normal component of the restriction of the velocity field. And the tangential component of the velocity field from the two sides determines how particle moves on the two sides. But the interface is formed only as a surface, and it does not really care how the particles on the boundary move on the two sides. So it is required that the normal component of the velocity fields on the two sides coincide, and that gives you the normal velocity of the interface. And the two fluid may not have the same density, so they may have different densities. So that is a natural reason why the tangential component most likely are different across the interface. And finally, in this problem, one has to consider the surface tension. So the jump of the pressure across the interface has to be proportional to the mean curvature. Here I take, so the mean curvature is a vector, but you can have the normal vector of the plus domain or the normal vector of the minus domain. So kappa plus is the dot product of the mean curvature with the outward normal vector of the plus domain, but the n plus and n minus differ just by a minus sign. So here we took the proportionality to be 1 because it has to be there. Without surface tension, the problem is ill-posed due to the Helmholtz instability. So the two problems eventually would be put in a very similar framework in the Lagrangian formulation, and they can be analyzed in pretty much the same way, in same recipe in the Lagrangian formulation, even though the outcome may be different concerning the Rayleigh-Taylor and the Helmholtz instability. So this is related to the instability I was talking about. So when we don't consider surface tension, then the problem can be ill-posed. This is due to the Rayleigh-Taylor instability and the Helmholtz instability explained on Wednesday by Didier. These instabilities were originally computed across a flat surface. That's easier to compute across a flat surface. And in the case of Rayleigh-Taylor instability, originally it was computed for stratified fluids, meaning that the density is not a constant. When the heavier fluid is on top of the lighter fluid, then the Rayleigh-Taylor instability appears. But the mechanism is that those create the wrong sign of the gradient of the pressure on the boundary, across the boundary. So here, when I say the Rayleigh-Taylor instability is in a slightly more general sense than the original meaning of the heavier fluid on top of the lighter fluid. Okay, so in this case, if you have a flat boundary and if you have a simple situation, you can do the explicit calculation. And then you see that for certain Fourier modes, you get the instability. And then when there is no surface tension, in the one fluid case, when the gradient of the pressure on the boundary has a wrong sign, then the Rayleigh-Taylor instability occurs for all high frequencies, for high wave numbers. And with the exponential growth rate proportional to k, which is the wave number. So it creates instability with unbounded exponential growth rate. So the linearized problem becomes ill-posed. So the Rayleigh-Taylor instability can cause the ill-posedness of the one fluid free boundary problem. And the same thing can be said for the Helmholtz instability, not the same thing. In the two fluid case, without surface tension, then instability can occur for all high wave numbers with the exponential growth rate proportional to k squared, roughly proportional to k squared as k goes to infinity. So they also cause unbounded exponential growth rate for higher wave numbers. So they also cause ill-posedness. So if you just analyze individual Fourier mode in some simple case when there is a flat boundary, then each of them can be solved and unstable, but putting them together, the linearized problem with infinite dimensional mode becomes ill-posed. But in particular, the Rayleigh-Taylor instability is only a possibility in the one fluid case without surface tension. And with two fluid, without surface tension, that always happens, okay? In particular, in the one fluid case, if the velocity field is irrotational, when there is no vorticity, then there's no Rayleigh-Taylor instability. And when you add the surface tension stabilizes. Physically, the physical intuition is that the surface tension is created by energy associated to the surface area. The surface area corresponds to a high regularity requirement. And so it's a stronger stabilizing effect in the high wave number and it overpowers the Kelvin-Helmholtz instability and the Rayleigh-Taylor instability and stabilizes the problem. And but one needs to see that in the analysis when the domain is moving, and also one needs to work with right coordinate to when you have a moving domain, you have to find a way to, when you do the analysis, you better find a way to somehow track the domain or fix the domain. And the popular choice is, of course, Lagrangian coordinates, but we're going to see whether that's the best coordinate system or not. Before I take the break, just to mention that there has been a lot of work on the well-posedness, local well-posedness, global well-posedness of the free boundary problem of the Euler equation, starting from 70s. And but the major breakthrough was in the 90s when Sijie Wu proved the local well-posedness in the rotational case in 2D and 3D. And later on, about 10 years ago, there had been the result on the global well-posedness or almost global well-posedness for irrotational small data. And these problems are handled, solved mainly by dispersive techniques. And then also there is the splash singularity obtained by the group of Castro, Cordova, Pfefferman, Conchedo, Gomez, Sereno, and so on. And Sijie also had a result when the surface might involve corners. Okay. That's a very nice result. And also recently, there had been result on the water wave problem when in the water wave problem when the free boundary touch the fixed boundary and form a corner in the fluid domain. This corner is different from this corner. In Sijie's work, the free surface might involve a corner, but here the corner is between the free surface and the fixed boundary. So there had been a lot of work in both one fluid, two fluid case, with or without surface tension, with or without vorticity, and so on. So after probably, can we?
So Chongchun, maybe now is a good time to take a break?
Yeah, that's what I was thinking.